In the early months of 1940, the Royal Air Force was pinning its strategic hopes on a twin-engine bomber known as the Avro Lancaster. It was an unmitigated mechanical disaster. The aircraft relied on the Rolls-Royce Vulture engine, a massively complex 24-cylinder power plant created essentially by bolting two V12 engines together around a single crankshaft. In practice, the Vulture notoriously snapped connecting rods under load, lost power at altitude, and had a terrifying tendency to catch fire in midair. Faced with a heavy bomber that was more dangerous to its own crews than to the enemy, the British aviation industry was thrown into a panic. Out of this catastrophic engineering dead end, Avro's chief designer Roy Chadwick salvaged the basic airframe, stretched the wing, and mounted 4 reliable Rolls-Royce Merlin engines instead. By abandoning a doomed engine architecture and pivoting to a 4-engine layout, Chadwick accidentally birthed the most devastating night bomber of the Second World War. At this exact moment in history, Britain found itself entirely isolated on the western edge of Europe, desperately searching for a way to strike back at the industrial heartland of Nazi Germany. The disastrous early daylight raids had proven that unescorted bombers were easy prey for German fighters and radar-directed anti-aircraft artillery. In response, Bomber Command shifted its entire doctrine to nighttime area bombing, a strategy born entirely of operational necessity rather than precision preference. Operating under the cover of darkness offered protection, but the early twin-engine bombers like the Vickers-Wellington lacked the payload capacity to inflict meaningful damage on sprawling industrial targets like the Ruhr Valley. The British military establishment realized that to cripple the German war machine, they needed a delivery system capable of hauling unprecedented tonnage across the freezing skies of northern Europe, navigating without visual references, and surviving long enough to do it again. If detailed breakdowns of aviation history and engineering interest you, subscribe. I've got plenty more of these deep dives coming. The solution was the Avro Lancaster, designated the Type 683, an aircraft whose entire engineering philosophy was built around one uninterrupted cavern of a bomb bay. Unlike the famous American Boeing B-17 Flying Fortress, which featured a heavily reinforced wing spar cutting directly through its fuselage and limiting the size of the bombs it could carry, the Lancaster was designed differently. Roy Chadwick designed the Lancaster's floor structure so that the immense 33-foot-long bomb bay was completely unobstructed. This specific structural choice was the defining characteristic of the aircraft. It meant that the Lancaster could carry a staggering internal payload of 14,000 pounds on a standard mission, compared to the 4,000 to 5,000 pounds typically carried by American daylight bombers. This unobstructed belly allowed the aircraft to carry the devastating 4,000-pound high-capacity blast bombs affectionately known as cookies, and later, massive bunker-busting munitions that no other Allied aircraft could physically accommodate. But this massive payload capacity required an airframe capable of generating immense lift and enduring heavy structural loads. The Lancaster was constructed as an all-metal, stressed-skin cantilever monoplane built largely of an aluminum alloy known as duralumin. To get this heavy airframe off the ground, it relied on 4 Rolls-Royce Merlin VA-12 liquid-cooled engines. Most operational Lancasters were fitted with the Merlin 24, or the American-built Packard Merlin 224 series, each generating roughly 1,600 horsepower at takeoff. The combination of these 4 supercharged engines gave the Lancaster an incredible power-to-weight ratio for a heavy bomber of its era. A fully loaded Lancaster would rumble down the runway weighing an astonishing 72,000 pounds, and by the end of the war, special modifications pushed that maximum takeoff weight to over 82,000 pounds. However, this raw lifting power and structural brilliance came with a hidden cost that drastically impacted the daily reality of the men flying it. To maximize the payload and keep the airframe as lightweight and aerodynamically clean as possible, the designers stripped away many of the defensive and ergonomic features that characterized heavy bombers from other nations. The cockpit of the Lancaster was surprisingly solitary. Unlike the American B-17 or B-24 Liberator, which utilized a pilot and a co-pilot sitting side by side with dual flight controls, the Lancaster featured only a single pilot. There was no co-pilot. Instead, a flight engineer sat on a collapsible jump seat beside the pilot, responsible for managing the complex fuel system, monitoring engine temperatures, and adjusting propeller pitch. If the pilot was severely wounded or killed during a mission, there was no secondary control column for another crew member to easily take over, meaning the crew had to rely on a rudimentary makeshift stick or immediately abandon the aircraft. The lack of a co-pilot was just one aspect of the incredibly austere environment inside the fuselage. The Lancaster was unpressurized, completely uninsulated, and deafeningly loud. At an operational altitude of 20,000 feet, the ambient temperature inside the aircraft frequently dropped to minus 40 degrees Fahrenheit. The 7-man crew, comprising the pilot, flight engineer, navigator, bomb aimer, wireless operator, mid-upper gunner, and rear gunner, relied on electrically heated flight suits just to stave off frostbite. The rear gunner endured the absolute worst of these conditions. Sitting in the extreme tail of the aircraft in a Fraser-Nash hydraulic turret, the rear gunner was effectively isolated from the rest of the crew for the entire 8-hour duration of a mission. To improve visibility in the dark, rear gunners often cut a large section of the perspex canopy away, exposing their face and chest directly to the freezing slipstream. This brings us to the defensive armament of the Lancaster, an area where early design choices severely handicapped the aircraft against evolving enemy tactics. The Lancaster was equipped with 3 power-operated turrets located in the nose, the dorsal mid-upper position, and the tail. These turrets housed a total of 8 Browning .303 caliber machine guns. When the aircraft was designed in the late 1930s, the fast-firing .303 was considered adequate for fending off unarmored biplanes. But by 1943, the skies over Germany were patrolled by heavily armored twin-engine night fighters like the Messerschmitt Bf-110 and the Junkers Ju-88. The rifle-caliber bullets of the Lancaster's defensive guns often bounced harmlessly off the thick armored windscreens of these night fighters, unless the British gunner managed a remarkably lucky shot into an engine block or fuel tank. Furthermore, the physical layout of the defensive turrets left a glaring blind spot that the German Luftwaffe exploited with devastating efficiency. Because the entire lower half of the Lancaster's fuselage was dedicated to that massive 33-foot bomb bay, there was no room for a ventral or belly turret. The underside of the Lancaster was completely blind and undefended. German night fighter pilots soon developed a tactic known as Schräge Musik, which involved mounting twin 20mm autocannons in the fuselage of their fighters, angled upward at roughly 60 degrees. A German pilot would use ground-based radar intercepts to find the bomber stream, stalk a Lancaster from below where the night sky hid them against the dark earth, and fire directly upward into the unprotected fuel tanks housed in the Lancaster's massive wings. The results of this upward firing tactic were catastrophic. Because the attackers aimed for the wings rather than the fuselage, the Lancaster's internal warning systems often went untriggered until the wing was entirely engulfed in flames. A burning wing meant the main spar would quickly fail, causing the aircraft to tumble violently out of the sky. This structural vulnerability highlighted another grim engineering flaw of the Lancaster, its escape hatches. The primary escape route for the crew in the forward section of the aircraft was a small rectangular hatch in the floor of the bomb aimer's compartment, measuring a mere 22 inches by 26 inches. Navigating this tiny aperture in total darkness, while wearing thick, electrically heated flight gear and carrying a bulky parachute, was incredibly difficult. If the aircraft was spinning out of control under high gravitational forces, it became nearly impossible. Consequently, the crew survival rate for a shot-down Lancaster was roughly 15%, a grim statistic that was significantly lower than the nearly 29% survival rate of its British contemporary, the Handley Page Halifax. Despite these glaring defensive and structural vulnerabilities, the offensive capability of the Lancaster kept it at the absolute forefront of the strategic bombing campaign. To improve the accuracy of night bombing and increase the survivability of the bomber streams, the British pioneered several cutting-edge avionics systems that turned the Lancaster into an electronic warfare platform. Early navigation relied heavily on a system called G, which used synchronized radio pulses transmitted from ground stations in England to provide navigators with intersecting grid lines. It was highly accurate, but its range was limited by the curvature of the Earth, meaning it degraded just as the bombers entered heavily defended German airspace. To compensate, scientists developed an airborne ground mapping radar known as H2S. The H2S system was an incredible technological leap for the early 1940s. It utilized a cavity magnetron to project high-frequency radar pulses downward, which then bounced back to the aircraft. Water, open ground, and dense urban concrete all reflected the radar waves differently. These returns were painted onto a rudimentary cathode ray tube display at the navigator's station, allowing them to effectively see the outline of cities, coastlines, and rivers through thick cloud cover and total darkness. To house the rotating scanner, a large teardrop-shaped perspex radome was bolted to the belly of the Lancaster, slightly altering its aerodynamic profile. However, this technological advantage came with an immediate and deadly operational price. The H-2S system actively transmitted powerful electronic signals into the night sky, acting like a brilliant lighthouse beacon in the dark. German technicians quickly developed a passive radar receiver called Naxos, which they installed in their night fighters. Instead of blindly hunting in the dark, German pilots could simply tune in to the British H-2S emissions and follow the invisible beam directly to the specific Lancaster transmitting it. This back-and-forth escalation defined the operational reality of the Lancaster cruise over the notorious Ruhr Valley, an area British airmen darkly referred to as Happy Valley. Flying over the heavy industrial zones of Germany meant navigating a multi-layered gauntlet of defense. First came the master searchlights, radar-guided beams that would pierce the darkness and lock onto a single Lancaster. Once locked, dozens of slave searchlights would instantly converge on the bomber, blinding the crew and illuminating them for the anti-aircraft batteries below. Flak over these targets was rarely aimed at individual aircraft. Instead, German gunners utilized a box barrage, filling a specific grid of altitude and airspace with thousands of exploding 88mm shells. The concussion waves from near misses would violently throw the heavy Lancaster around the sky, shattering perspex, shredding the duralumin skin, and terrifying the crew. Knowing what you now know about its historical performance and the incredible dangers the crews faced, do you think this singular focus on maximum payload at the expense of defensive armor and crew escape systems was the right call for its era? Share your thoughts below. The Lancaster's ability to absorb punishment and keep flying was largely dependent on the incredible resilience of the Rolls-Royce Merlin engines and the robust construction of its main wing spar. While it was highly vulnerable to internal fires, the structural integrity of the airframe under normal kinetic damage was impressive. Ground crews routinely patched hundreds of jagged shrapnel holes with sheet metal and rivets between missions. The maintenance burden of keeping these complex four-engine aircraft operational in the harsh conditions of wartime England was staggering. Ground mechanics, armorers, and fitters often worked outdoors in freezing rain and deep mud, using rudimentary hoists to change thousands of spark plugs, replace entire engine blocks, and manually winch 4,000-pound bombs into the expansive belly of the aircraft. Without the tireless, freezing labor of these ground crews, the entire strategic night offensive would have ground to an absolute halt within weeks. Beyond standard strategic bombing, the Lancaster's unique lack of a central bomb bay spar made it the only aircraft in the Allied inventory capable of carrying out highly specialized, unconventional engineering attacks. The most famous of these was Operation Chastise, widely known as the Dambusters raid. To destroy the hydroelectric dams of the Ruhr Valley, British engineer Barnes Wallis designed the upkeep bouncing bomb, a massive cylindrical weapon designed to skip across the surface of the water, sink against the face of the dam, and detonate under hydrostatic pressure. To deliver this weapon, Avro created the Type 4-6-4 provisioning Lancaster. They completely removed the standard bomb bay doors, installed heavy V-shaped struts to hold the cylinder, and added a hydraulic motor to spin the weapon backward at 500 revolutions per minute prior to the drop. Delivering the upkeep weapon required exceptional flying skills and an absurd level of precision. The aircraft had to be flown at exactly 232 miles per hour, at precisely 60 feet above the dark water of the reservoir. Standard pressure altimeters of the era were wildly inaccurate at such low levels. To solve this, engineers mounted 2 spotlight lamps on the underside of the Lancaster, angling them so that their beams would intersect perfectly on the surface of the water when the aircraft was exactly 60 feet high. The pilot, Guy Gibson, and his squadron had to fly massive 4-engine heavy bombers into heavily defended valleys at night, using analog spotlights to maintain altitude while taking intense anti-aircraft fire. It was a feat of raw aviation skill that pushed the structural capabilities of the Lancaster and the psychological endurance of its crews to the absolute breaking point. As the war progressed, Barnes Wallis continued to design even larger conventional munitions, which further solidified the Lancaster's historical legacy as the ultimate heavy lifter. He developed the 12,000-pound tall boy and the staggering 22,000-pound Grand Slam earthquake bombs. These aerodynamically streamlined monsters were designed to be dropped from high altitudes, exceeding 20,000 feet. They featured offset tail fins that caused the bomb to spin as it fell, stabilizing its flight and allowing it to break the sound barrier before impact. Instead of destroying a target with a surface blast, these bombs penetrated deep into the earth or concrete before detonating, creating an artificial localized earthquake that collapsed submarine pens, railway viaducts, and deeply buried bunkers. Only heavily modified Lancasters, stripped of their gun turrets and excess weight, with their bomb bay doors entirely removed to accommodate the massive girth of the weapons, could deliver these war-ending blows. When comparing the Lancaster to its contemporaries, its historical role becomes starkly defined. The Handley Page Halifax was a more forgiving aircraft to fly and offered far better survival chances for a bailing crew, but it could not match the raw tonnage or the altitude performance of the Lancaster. The American Boeing B-17 was vastly superior at defending itself during daylight precision raids, bristles with 50 caliber machine guns, and featured a far more robust crew survivability rate, but its internal payload was a fraction of the British machine. The Lancaster was not a precision instrument, it was a blunt, overwhelming sledgehammer designed to systematically level entire cities and eradicate heavy industry under the cover of darkness. By 1944, streams of over 800 Lancasters were frequently marshaled for single operations, unleashing firestorms that completely consumed cities like Hamburg and Dresden. This operational reality leaves the Avro Lancaster with a complex and often debated historical legacy. The strategy of area bombing, forcefully championed by Air Chief Marshal Arthur Harris, was explicitly designed to dehouse the German workforce and break the psychological will of the enemy. It resulted in horrific civilian casualties and intense post-war moral scrutiny. Yet, from a purely strategic and industrial perspective, the night bombing campaign fundamentally fractured the German war economy. It forced the Nazi high command to divert millions of personnel, thousands of anti-aircraft artillery pieces, and vast quantities of aviation fuel away from the Eastern Front and the Normandy beaches to defend the skies over the homeland. The Lancaster was the primary tool that executed this grim arithmetic of attrition. The human cost paid to operate this machine was staggeringly high. Over 55,000 men of Bomber Command perished in the skies over Europe, a catastrophic mortality rate that exceeded almost every other branch of the Allied military forces. The men who flew the Lancaster were intimately aware of its flaws, the freezing cold of its aluminum hull, the inadequacy of its defensive armament, and the terrifying difficulty of escaping it in an emergency. Yet, they consistently climbed into its dark fuselage night after night because it was the only weapon capable of striking the heart of an empire that had engulfed Europe in tyranny. The Avro Lancaster remains a masterpiece of utilitarian wartime engineering, an aircraft born from a failed engine project that was violently shaped by the desperate necessities of its era to become the most destructive conventional weapon ever built by the British Empire. If you found this historical analysis useful, a like helps more people discover these deep dives. Thanks for watching.